Streaming success. Unveiling Apache Kafka for modern data architectures. 1. The data deluge and the need for streams. Think about your average day. Every click on your phone, every online purchase, every tap of your contactless payment, every interaction with a smart device in your home, and every message you send. All these actions generate data. If you're a business, multiply that by millions of customers, thousands of employees, and countless connected devices. The sheer volume of information being created around us is staggering. It's not just data sitting still in databases, waiting to be retrieved. It's data that's constantly being born, constantly moving, and constantly changing. This ceaseless stream of information has become a defining characteristic of our modern world. From weather sensors churning out readings every second, to financial trading systems executing millions of transactions, to social media platforms handling billions of posts and interactions, we are experiencing what can only be described as a data deluge. The challenge is no longer just how to collect all this data, but how to make sense of it, derive insights from it, and react to it as it happens. It's like trying to drink from a fire hose. If you're not equipped, you'll be overwhelmed. 1.1 The ubiquity of data, a modern challenge. In the digital age, data is everywhere, and it's always in motion. Imagine data not as static files neatly organized in binders, but as a ceaseless, ever-flowing river. Every interaction, every measurement, every update adds to its current. This river of data is characterized by what experts often call the 3 V's. Volume. The sheer amount of data being generated is immense. Think of every search query entered into a search engine, every video uploaded to a streaming service, or every log record from a vast network of servers. We're talking terabytes, petabytes, and even exabytes of information. Velocity. Data is being created and needs to be processed with incredible speed. In many scenarios, waiting means losing an opportunity. Automated cars produce gigabytes of sensor data per minute, financial markets demand insights in milliseconds, and online retailers need to react to shopping trends in real time. Variety. Data comes in many forms. It can be structured, like customer records in a database, semi-structured, like a social media post with hashtags, or unstructured, like an image or a video. Dealing with this diverse landscape adds complexity. The real challenge isn't just that these 3 V's exist. It's that to truly leverage this data, we need to operate on it quickly and efficiently. We need to go beyond simply collecting it, to acting on it, to use its fluidity to our advantage. 1.2 The limitations of traditional data processing. For a long time, the dominant approach to dealing with large amounts of data was batch processing. This meant collecting data over a period, perhaps an hour, a day, or even a week, and then processing it all at once in a large batch. To understand this, imagine a traditional daily postal service. All the mail for the day is collected, taken to a central sorting facility, processed overnight, and then delivered the next morning. It's an efficient system for its purpose, but it has a built-in delay. If you send a letter at noon, it won't be read until the next day at the earliest. In the world of data, this translates to delayed insights. If you're a business trying to detect fraudulent transactions, waiting until the next day to analyze suspicious activity could result in significant losses. If you're an online store, waiting to process customer click data means you miss the opportunity to offer real-time recommendations when they're still browsing. Stale information. By the time batch processed data yields insights, the underlying situation might have changed. Decisions made on yesterday's data can quickly become irrelevant in a fast-paced environment. Complex connections. Often, different parts of an organization would collect and process their data in separate silos. Connecting these silos meant creating numerous, often fragile, point-to-point integrations. A tangled web that became increasingly difficult to manage as more systems were added. This often led to a lack of a unified, real-time view of the business. While batch processing remains crucial for certain tasks, like long-term historical reporting or large-scale data warehousing, its limitations become glaringly obvious when speed and immediacy are paramount. In the age of instant gratification and hyperconnectivity, businesses and systems need to react to events as they unfold, not hours or days later. 1.3 The rise of real-time and event-driven architectures. The recognition of these limitations paved the way for a revolutionary shift: the move towards real-time and event-driven architectures. Instead of processing data in large chunks, the idea is to process individual pieces of data, which we call events, as they occur. An event is simply a record of something that happened at a specific point in time. It could be a customer logging into an app, a sensor reporting a temperature change, a financial transaction being confirmed, or a machine completing a task. Each event is a concise, immutable fact about a particular moment in time. To reuse our postal service analogy, instead of waiting for a daily pickup, imagine a modern delivery service where each parcel, an event, is immediately logged, routed, and sent on its way the moment it arrives at the sorting facility. There's no waiting for a batch. Every item is handled as soon as it appears. This shift delivers immense benefits: immediate insights and actions. Fraud can be detected in real time, personalized recommendations can be offered as a customer browses, and system anomalies can be flagged the moment they occur. Enhanced user experience. Think of instant updates on stock prices, real-time tracking of a food delivery, or dynamic content tailored to your current activity. All of these are powered by event-driven systems. Agility and responsiveness. Businesses can react almost instantly to market changes, customer behavior, or operational issues, gaining a significant competitive edge. The demand for such agility is no longer just a luxury. It's a necessity for modern organizations. But building these systems effectively means we need a new kind of infrastructure, one that can handle the sheer volume and velocity of events reliably. 1.4. Introducing the need for a central nervous system for data. As more systems begin to generate and consume events in real time, the challenge shifts from isolated data silos to managing a vast, interconnected web of flowing information. If every application and service tries to connect directly to every other application needing its data, we quickly return to the tangled mess of point-to-point integrations, but at an even greater scale. What's needed is a neutral, central conduit, a highly robust, scalable, and reliable platform that can act as the nerve center for all these events. It needs to ingest enormous amounts of data from diverse sources without breaking a sweat. Store this data durably, ensuring that no event is lost, even if systems falter. Allow many different applications to read from the data streams simultaneously, at their own pace, without interfering with each other. Enable real-time transformations and analysis of the data as it flows. Imagine the human body's central nervous system. It efficiently transmits signals, events, from every part of the body to the brain and back, ensuring synchronized and effective bodily functions. It's not a single point of failure. It's a distributed network that routes critical information precisely and reliably. This is precisely the problem that Apache Kafka was designed to solve. It provides the foundational infrastructure, the central nervous system, for moving, storing, and processing this data in motion efficiently and reliably. It's the technology that makes the dream of real-time, event-driven architectures a practical reality, enabling businesses and applications to truly operate at the speed of data. In the following chapters, we will unveil exactly what Apache Kafka is and how it empowers this transformation. 2. What is Apache Kafka? A bird's eye view. In the previous chapter, we established that the world is flooded with data, constantly moving, and that there's a critical need for systems that can process this data in motion in real time. We also saw how traditional methods fall short when immediacy is paramount. This brings us to Apache Kafka, a technology that has rapidly become the cornerstone for real-time data architectures worldwide. But what exactly is it? For many coming across it for the first time, Apache Kafka can be a bit of a chameleon. Is it a database, a message queue, a batch processing system? The truth is, it shares some characteristics with all of these, but it fundamentally redefines them, creating something unique and incredibly powerful. 2.1 More than just a message queue, a paradigm shift. A common misconception is that Kafka is simply another message queue, like RabbitMQ or ActiveMQ. While it can act as a message queue, this view gravely underestimates its capabilities. Traditional message queues are often designed for point-to-point communication where a message is sent, read by one consumer or a small group that shares the load, and then typically deleted from the queue. They prioritize immediate delivery and often discard messages after consumption. Consider the difference. Traditional message queue, imagine sending a letter to a friend. Once your friend receives and reads the letter, it has served its purpose. Other friends don't get to read that specific letter unless you send them each a copy. The letter is gone from the mailbox once retrieved. Apache Kafka. Imagine publishing an article in a specialized journal or logging an entry in a universal ledger. That article or entry persists. Many different people can subscribe to the journal or read the ledger at different times, and each can read the entire content from any point they choose without affecting what others can read. The information is not deleted after being read. It remains available for a configurable period, typically days or weeks, but often much longer. This distinction is crucial. Kafka's design allows many different applications to independently access the same stream of data, without requiring them to know about each other or to interfere with each other's processing. This makes it a central nervous system, connecting disparate parts of an organization's data infrastructure. It's a paradigm shift from transient messages to persistent streams of events. 2.2 Kafka's core identity. A distributed commit log. At its heart, Apache Kafka is best understood as a distributed commit log. This concept is fundamental to grasping its immense power and versatility. Think of a commit log, sometimes called a transaction log or a write-ahead log, like the meticulous record-keeping found in a bank or an accounting firm. Every single transaction or event is appended, in strict order, to the end of a master list. Once an entry is written into this ledger, it's immutable, it cannot be changed or removed. New entries are always added at the end. Now, add the word distributed, and you have Kafka. It's not just one ledger. It's a ledger that can be spread across many different servers, or nodes, in a cluster. This distribution is key to its ability to handle enormous volumes of data and to stay available even if some servers fail. Kafka was originally developed at LinkedIn to track user activity data, page views, clicks, searches, etc., at a massive scale. Their existing systems couldn't keep up with the torrent of data. They needed something that could ingest billions of events a day reliably and make them available to hundreds of different applications for real-time analysis, personalization, and monitoring. The distributed commit log model was the elegant solution. This append-only, immutable nature means that once an event is recorded in Kafka, it's there for good, for at least as long as you configure it to be. This provides incredibly strong durability guarantees and allows for a wide range of sophisticated use cases that go far beyond simple messaging. 2.3 Key principles and guarantees that set Kafka apart. The design as a distributed commit log underpins several critical strengths of Apache Kafka. Scalability. Because the commit log can be distributed across many servers, Kafka can scale horizontally. This means you can increase its capacity by simply adding more machines to your Kafka cluster. This allows it to handle astounding volumes of data and millions of events per second, growing with your needs from a small setup to a vast enterprise-wide backbone. Durability and fault tolerance. Data written to Kafka is not ephemeral. It's stored safely on disk and, crucially, replicated across multiple servers. This replication ensures that if one server fails, your data isn't lost and the system remains operational. It's like having multiple identical copies of that valuable ledger stored in different secure locations. High throughput and low latency. Kafka is engineered for speed. It leverages efficient disk, I/O, and network protocols to achieve extremely high rates of data ingestion, throughput, while maintaining very short delays, latency, between an event being published and it becoming available for consumption. This makes it ideal for applications where real-time performance is paramount. Multiple consumers. As hinted earlier, any number of independent applications can read from the same stream of data in Kafka without affecting each other. One application might be analyzing website clicks for real-time recommendations, another archiving them for long-term analytics, and a third updating a user profile, all reading from the same source data at their own pace. These fundamental properties make Kafka uniquely suited to be the central nervous system for modern data architectures, providing a robust and reliable foundation for capturing and distributing real-time information. 2.4. The three core capabilities of Apache Kafka. To summarize, Apache Kafka is not just one thing. It embodies three core capabilities that, when combined, make it an incredibly versatile and powerful platform. Publish, write, and subscribe read to streams of records. This is its messaging capability. Applications can send data publish to Kafka, and other applications can receive that data, subscribe. It acts as a highly efficient, high-volume broadcast system for data. Store streams of records. Unlike traditional queues that discard messages, Kafka durably stores records for a configurable period, e.g., a week, a month, or even indefinitely. This persistent storage is what makes it a log and allows applications to reread historical data or catch up if they've been offline. Process streams of records. While core Kafka moves and stores data, its ecosystem provides robust tools, which we'll explore in later chapters, to transform, aggregate, join, and analyze these streams of records in real time. This elevates Kafka from a simple data transport to a full-fledged stream processing platform. These three pillars collectively explain why Kafka has become so indispensable. It's the foundational technology that enables businesses to truly embrace the fluidity of data, turning the data deluge from a challenge into an endless wellspring of real-time insights and opportunities. In the next chapter, we'll break down the specific components that make up a basic Kafka system and how they work together. 3. The building blocks: producers, consumers, topics, and brokers. Now that we have a bird's-eye view of Apache Kafka as a distributed streaming platform, let's peel back another layer and look at its core components. Understanding these fundamental building blocks is essential for grasping how Kafka works and how it manages to move and store data with such remarkable efficiency and reliability. Imagine Kafka as a highly sophisticated, automated postal service designed to handle a massive volume of mail, ensuring it's always delivered reliably and accessible when needed. This analogy will help us map the technical terms to more familiar concepts. 3.1. The Kafka ecosystem, a conceptual overview. At a high level, a Kafka system involves several key players. Producers. These are the senders of data. They are applications or services that create events and publish them to Kafka. Consumers. These are the receivers of data. They are applications or services that read events from Kafka to process them. Topics. These are categories or feeds where data streams are organized within Kafka. Producers publish to topics and consumers read from topics. Brokers. These are the actual servers that run the Kafka software. They form a Kafka cluster and are responsible for storing topic data, serving requests from producers and consumers, and replicating data. All these components work together in a finely tuned choreography to ensure that data flows seamlessly and without interruption. Let's look at each in more detail. 3.2. Producers, the data senders. Think of a producer as someone writing a letter or packaging an item and dropping it into a specific mailbox. The person sending the mail doesn't necessarily know or care about the intricate routing details or how the mail is physically transported. They just need to ensure it gets into the correct mailbox destined for the intended recipient. In Kafka, a producer is any application or service that generates data and sends it to a Kafka topic. These events could be anything: a user clicking a button on a website, a temperature reading from an IoT sensor, a financial transaction, a log message from a server, or an update to a customer's profile. When a producer sends an event, it typically specifies the topic, which category of data this event belongs to. For example, a web click might go to a website clicks topic, while a payment event goes to a payment transactions topic. The message key, optional but important, a value that helps Kafka decide where to store the event within that topic. Using a key can ensure that all events related to the same thing, e.g., all events for a specific user or all temperature readings from a specific sensor, are processed in order. We'll discuss this more when we talk about partitions in a later chapter. The value, the actual data payload of the event itself. Producers are built for high throughput and reliability. They can send events individually or batch them together for more efficient network use. They can also be configured to wait for acknowledgments from Kafka, ensuring that the data has been safely received and stored before continuing, providing a guarantee against data loss. 3.3 Consumers, the data receivers. If producers are the senders, consumers are the receivers. A consumer is an application or service that reads events from one or more Kafka topics to process them. Continuing our postal analogy, a consumer is like someone checking their mailbox and reading the letters or retrieving their packages. However, Kafka consumers have a crucial feature that sets them apart from simple mail retrieval: the concept of consumer groups. Imagine you have a massive influx of mail events that needs to be sorted and processed quickly. If you have only one person sorting, they might get overwhelmed. So, you bring in a team of sorters. This team is a consumer group. Here's how a consumer group works: shared workload. All consumers within the same consumer group work together to process the events from a topic. No duplication. Each event from the topic is processed by only one consumer within that specific group. This ensures that the work is distributed efficiently and you don't process the same event multiple times by mistake within the same logical application. Independent reading. Different consumer groups can read from the same topic independently. If you have a separate team in another room doing a different kind of mail processing, they can also read all the mail from the beginning without affecting the first team. This is a core strength of Kafka, one stream of data serving many different applications. Consumers are also vital for keeping track of what they've read. Each consumer, or rather, each consumer within a group for a specific topic, remembers its offset. The offset is simply the position it has reached in the topic's log. This is like a bookmark in a book. If the consumer application stops or crashes when it restarts, it knows exactly where it left off and can resume reading from that exact point, ensuring no data is missed or reprocessed unnecessarily. 3.4 Topics, the categories of data. Topics are the fundamental way Kafka organizes data. Think of them as specific channels or categories for data streams. If producers are dispatching different types of mail, topics are the specially designated mailboxes for each type. For example, all events related to user signups might go to a user signups topic. All sensor readings from a climate control system might go to a building sensors topic. A social media platform might have topics like user posts, likes, or comments. Key characteristics of topics: named categories. Each topic has a unique name. Publish-subscribe. Producers publish events to specific topics, and consumers subscribe to specific topics to receive events. Separation of concerns. Topics provide a clean way to separate different streams of data, ensuring that applications interested in one type of event don't have to wade through irrelevant data from other streams. Immutable log. Once an event is written to a topic, it's appended to the end of its log and cannot be changed. It remains available for a configured period, e.g., 7 days, 30 days, or even indefinitely, after which it is automatically deleted. Crucially, topics are themselves divided into partitions, which we will discuss in detail in the next chapter. Partitions are how Kafka achieves its incredible scalability and allows for parallel processing. For now, understand that a topic is a logical stream of related events. 3.5 Brokers, the Kafka servers. Finally, we have the brokers. These are the actual servers that run the Kafka software. They are the physical infrastructure of our postal service analogy, the mail sorting centers, post offices, and mail trucks themselves. A Kafka cluster typically consists of one or more brokers working together. For resilience and scalability, most production Kafka deployments will use multiple brokers. Each broker is responsible for storing topic data. Brokers store the events for the topics and their partitions that they are assigned to. Serving client requests. They handle requests from producers to write events and consumers to read events. Replication. They manage the replication of topic data to other brokers to ensure fault tolerance. If one broker goes down, its data is still available on another broker. Coordination. In older versions of Kafka, brokers relied on another service called Apache Zookeeper for coordination. Newer versions, however, are moving towards eliminating this external dependency, as we'll see. When producers send events, they send them to the Kafka cluster, which then routes them to the appropriate brokers that host the target topic's partitions. Similarly, consumers connect to the brokers to fetch the events they want to read. Together, producers, consumers, topics, and brokers form the fundamental anatomy of an Apache Kafka system. Understanding their individual roles and how they interact provides the groundwork for appreciating Kafka's architectural elegance and its ability to handle immense volumes of real-time data flow with remarkable reliability and performance. In the next chapter, we'll dive deeper into how Kafka uses partitions and replicas to achieve its impressive scalability and fault tolerance. 4 Under the hood: partitions, replicas, and distributed systems. In the previous chapter, we introduced the fundamental components of Kafka: producers, consumers, topics, and brokers. We briefly touched upon the idea that topics are divided into something called partitions, and that brokers handle replication. These two concepts, partitions and replicas, are absolutely central to Kafka's design. They are the mechanisms that allow Kafka to be incredibly scalable, highly available, and fault-tolerant. Let's pull back the curtain a bit further and explore how these elements work together to form a robust distributed system. 4.1 Partitions: the secret to Kafka's scalability. We learned that a topic is a logical category for a stream of events. But how does Kafka handle a topic that might have millions or even billions of events flowing through it every day? The answer lies in partitions. A topic is divided into one or more partitions. Each partition is an ordered, immutable sequence of events, much like our commit log analogy. When a producer sends an event to a topic, that event is appended to one of the topic's partitions. Think of it this way. If a topic is a single very long, continuous historical ledger, a partition is like breaking that single ledger into several smaller, independent, but still ordered mini-ledgers. Imagine our postal service analogy again. If a letters topic is our main pile of incoming mail, instead of having one huge sorting table for all letters, we set up several smaller, independent sorting tables, each handling a specific portion of the mail. Each of these smaller tables is a partition. Here's why partitions are so powerful. Parallelism for producers. Producers can write events to different partitions of the same topic simultaneously. This allows Kafka to handle a very high rate of incoming data across multiple brokers. Instead of one large choke point, you have multiple parallel entry points. Parallelism for consumers. Consumers within a consumer group can also read from different partitions in parallel. If a topic has 10 partitions, a consumer group can have up to 10 consumers, each processing one partition independently. This massively increases the rate at which data can be consumed and processed. It's like having multiple clerks at our postal service, each dedicated to sorting and processing mail from a specific sorting table. Load distribution. Different partitions of a topic can be hosted on different Kafka brokers. This distributes the storage and processing load across the entire Kafka cluster. If you have a topic with 10 partitions and 3 brokers, Kafka will distribute those partitions across the brokers, maximizing resource utilization. How does an event get assigned to a partition? When a producer sends an event, Kafka, or the producer itself, configured appropriately, decides which partition that event will go into, with a key. If the producer provides a key for the event, e.g., a userid, a productid, or a sensorid, Kafka ensures that all events with the same key always go to the same partition. This is crucial for maintaining the order of related events. For example, all updates for useray will always arrive in the same order in the same partition, without a key. If no key is provided, events are typically distributed among partitions in a round-robin fashion. This ensures an even distribution of data across all partitions, maximizing throughput. The number of partitions in a topic is a crucial design decision. Too few, and you might limit scalability. Too many, and it can add overhead. 4.2 Replicas. Ensuring durability and high availability. While partitions give us scalability, what happens if a broker, one of our Kafka servers, suddenly crashes? If a partition lives on only one broker, then that partition and the data it contains would become unavailable or even lost. This is where replication comes in. To ensure data durability and system availability, Kafka replicates partitions across multiple brokers. Each partition has a designated number of replicas. If a topic has a replication factor of 3, each partition will have 3 copies, 1 leader replica and 2 follower replicas. Leader replica. For each partition, one of its replicas is designated as the leader. All producers wishing to write to that partition and all consumers wishing to read from it will communicate only with the leader replica. This ensures consistency. The leader is responsible for accepting writes and reads for its partition. Follower replicas, the other replicas for that partition, are followers. They passively copy the data from the leader. Their job is to stay perfectly synchronized with the leader, receiving and applying all new events in the same order. Think of it like this. For each of our mini-ledgers, partitions, we designate one clerk as the lead clerk, who handles all incoming mail and all requests to view the mail. This lead clerk also has one or more deputy clerks, followers, who meticulously copy everything the lead clerk does in real time. Here's why replication is vital: fault tolerance. If the broker hosting the leader replica for a partition fails, Kafka will automatically elect one of the follower replicas to become the new leader. This process is very fast, minimizing downtime and ensuring that data flow can continue uninterrupted. The deputy clerk immediately steps up to become the new lead clerk, and operations proceed. Durability. Because data is copied across multiple brokers, even if an entire broker is lost, e.g., due to hardware failure, the data on its partitions isn't lost. The other replicas still hold a complete copy. High availability. Producers and consumers can continue operating even when individual brokers fail, thanks to the automatic leader election process. The number of replicas, often called the replication factor, determines how many copies of each partition exist. A common replication factor is 3, meaning 2 followers for every leader. This provides good fault tolerance, as the system can tolerate the failure of 2 brokers containing 2 replicas of a single partition and still maintain a copy. 4.3 Putting it together. A distributed system. So, when you create a Kafka topic, you specify 2 key numbers: number of partitions, how many segments to divide the topic into; replication factor, how many copies of each segment to maintain across different brokers. Let's illustrate with an example. Suppose you have a Kafka cluster with 3 brokers, broker A, broker B, broker C, and you create a topic called web clicks with 3 partitions and a replication factor of 3. Partition 0. Leader on broker A, followers on broker B and C partition 1. Leader on broker B, followers on broker C and A partition 2. Leader on broker C, followers on broker A and B now. If a producer sends an event for web clicks with a specific user ID key, it always goes to, say, partition 0, leader on broker A. If broker A suddenly crashes, Kafka detects this, and either broker B or broker C will be elected as the new leader for partition 0. Producers and consumers will automatically switch to communicating with the new leader. Data flow continues. All this happens largely transparently to the applications using Kafka. This sophisticated interplay of partitions, for horizontal scaling and parallelism, and replicas, for fault tolerance and durability, is what makes Kafka a powerhouse for distributed stream processing. It's a meticulously engineered system designed to handle the data deluge of modern applications with resilience and speed. In the next chapter, we'll see how Kafka used to rely on another crucial component, Apache Zookeeper, to coordinate all these distributed efforts, and how that relationship is evolving. 5. Zookeeper in Kafka, the unseen architect. In the previous chapter, we delved into the core mechanisms of partitions and replicas that enable Kafka's scalability and fault tolerance. These are complex, dynamic interactions, brokers identifying leaders, electing new ones when failures occur, and ensuring all replicas stay in sync. How do all the individual Kafka brokers know who the leader is for each partition? How do they discover newly added brokers or topics? Who keeps track of the overall state of the Kafka cluster? For many years, the answer to these questions pointed to another fundamental Apache project, Apache Zookeeper. Zookeeper acted as the unseen architect, or the chief coordinator, for the Kafka cluster, centralizing critical metadata and facilitating crucial operations. 5.1 What is Apache Zookeeper? A conceptual overview. Before we dive into its role with Kafka, let's understand Zookeeper itself. At its core, Apache Zookeeper is a distributed open-source coordination service for distributed applications. Think of it as a highly reliable, centralized system for storing and managing configuration information, naming, providing distributed synchronization, and offering group services. Imagine you have a complex project with many independent teams working simultaneously, your distributed applications. Each team needs to know the current project status, who is leading which subtask, what resources are available, and if any team members have gone offline. Zookeeper provides a single, consistent, and highly available source of truth for all this shared state information. Key characteristics of Zookeeper: hierarchical namespace. Data in Zookeeper is organized in a file system-like hierarchy called znodes, Zookeeper nodes. Each znode can store data and have child znodes. Highly available. Like Kafka, Zookeeper runs as a cluster of servers, called an ensemble, and uses a consensus protocol, ZAB protocol, to ensure data consistency and fault tolerance. If one Zookeeper server fails, the ensemble continues to operate. Watch mechanism. Clients like Kafka brokers can watch znodes for changes. When a znode's data changes or its children are updated, the watching client is immediately notified. This is crucial for dynamic cluster management. 5.2 Zookeeper's responsibilities in Kafka pre-Kraft. Historically, in most Kafka deployments, Zookeeper was an absolute necessity. Kafka brokers implicitly relied on a Zookeeper ensemble for several critical functions. Broker registration. When a Kafka broker starts, it registers itself with Zookeeper. This allows other brokers, producers, and consumers to discover which brokers are online and available in the cluster. It's like each postal office reporting its status to a central directory. Controller election. In every Kafka cluster, there's one broker designated as the controller. The controller broker is responsible for important administrative tasks, such as managing the state of partitions and replicas, handling leadership elections for partitions when a broker fails, and performing topic creations deletions. Zookeeper facilitates the election of this controller. If the current controller goes down, Zookeeper helps elect a new one from the remaining healthy brokers. Topic metadata. Information about topics, like their names, number of partitions, and replication factor, and where each partition's leaders and followers reside across the brokers, was stored in Zookeeper. Configuration management. Various Kafka configurations and access control lists, ACLS, were also stored and managed by Zookeeper. Essentially, Zookeeper served as the glue that held the distributed Kafka cluster together, providing the coordination and metadata store that enabled Kafka to function as a unified, resilient system. If your Zookeeper ensemble went down, your Kafka cluster would eventually grind to a halt or become unstable, even if the Kafka brokers themselves were still running. This tight coupling meant that managing a Kafka cluster also involved managing a separate Zookeeper cluster, adding operational overhead and complexity. 5.3 The evolution. Enter Kraft, Kafka Raft metadata. While critical, the dependency on Zookeeper presented several challenges. Operational complexity. Running and maintaining a separate Zookeeper cluster adds overhead. It requires its own set of expertise, monitoring, and scaling considerations. Performance bottlenecks. For very large Kafka clusters with thousands of partitions and brokers, the amount of metadata managed by Zookeeper could sometimes become a performance bottleneck. Version mismatches. Keeping Kafka and Zookeeper versions compatible could be tricky during upgrades. Recognizing these issues, the Kafka community embarked on a significant architectural evolution. Project Kraft, Kafka Raft metadata. Kraft's goal: to remove the dependency on Zookeeper by integrating the metadata management directly into Kafka itself. This is achieved by having a set of Kafka brokers take on the role of a controller and use a new consensus protocol based on the Raft algorithm, similar to Paxos or Zookeeper ZAB. How Kraft changes things. Consolidated cluster. With Kraft, there's no separate Zookeeper cluster to manage. Kafka brokers themselves form the metadata quorum, coordinating and maintaining the cluster state. simplified operations. Deploying, scaling, and managing Kafka becomes simpler, as you only have one type of component, Kafka brokers, to worry about. Improved scalability. The Raft-based metadata management is designed to be more scalable and efficient, especially for huge clusters, as it leverages Kafka's own robust messaging layer for metadata replication. Faster failover. Controller failover times are expected to be significantly faster, improving overall cluster resilience. The transition. Kraft has been undergoing a phased introduction. While Zookeeper-backed Kafka is still widely used and supported, newer versions of Kafka, starting with specific releases and maturing over time, now offer Kraft mode as an option. Eventually, Kraft will become the default and recommended way to operate Kafka, phasing out the Zookeeper dependency entirely for new deployments. In summary, Apache Zookeeper played a vital, albeit often unseen, role in coordinating Kafka clusters for many years, acting as the centralized brain for distributed metadata. Its responsibilities ranged from broker registration and controller election to storing topic configurations. However, the operational complexities and scalability limitations it introduced led to the ambitious Kraft project, which is gradually internalizing these coordination capabilities directly within Kafka brokers. This evolution simplifies operations and paves the way for even larger, more resilient Kafka deployments in the future. 6. Ensuring data integrity. Guarantees, durability, and delivery semantics. One of the most critical aspects of any data system is trust. Can you trust that the data you send will actually be received and stored? Can you trust that once stored, it won't be lost? And can you trust that when you read the data, you're getting exactly what you expect? In the world of real-time data streams, these questions become even more paramount. Apache Kafka is designed with strong guarantees regarding data integrity, durability, and delivery. While no distributed system can offer absolute, mathematically provable perfection in all scenarios due to the inherent complexities of networks and hardware, Kafka provides exceptional levels of reliability and flexibility that are more than sufficient for the vast majority of real-world applications. Understanding these guarantees is key to building robust and trustworthy streaming applications. 6.1. Data durability. Kafka's persistence promise. At its core, Kafka is built around the concept of a distributed, immutable log. This means that once an event, or record, is written to a Kafka topics partition, it's appended to the end and cannot be changed or deleted. New events are always added, making it an append-only system. Persist to disk. Every event published to Kafka is immediately written to disk on the Kafka brokers. This is a fundamental aspect of its durability. Even if a broker crashes, the data already saved to its disks will be recovered when the broker restarts. Controlled retention. Events are retained in Kafka topics for a configurable period, known as the retention policy. This could be anything from a few hours to several days, weeks, or even indefinitely. This policy is set per topic. Once an event's retention period expires, it is automatically removed by Kafka. This feature means that unlike traditional message queues, older events are not immediately discarded after being consumed. They remain available for other consumers or for reprocessing. Replication for resilience. As we discussed in Chapter 4, each partition of a topic is replicated across multiple brokers. If one broker fails, the data for its partitions is still available on the other replicas. This multi-copy approach is the primary mechanism for ensuring high durability and fault tolerance. The combination of writing to disk and replicating across multiple brokers provides a robust guarantee that once Kafka acknowledges receiving an event, that event is highly unlikely to be lost. 6.2. Producer guarantees. Configuring acknowledgements, ACKs. When a producer sends an event to Kafka, it needs to know if that event was successfully received and persisted. Kafka offers different levels of acknowledgement guarantees, which producers can configure. ACKs equals 0, fire and forget. The producer sends the event and doesn't wait for any acknowledgement from the Kafka broker. Analogy, tossing a message in a bottle into the ocean. You hope it gets there, but you don't wait for confirmation. When to use? This provides the highest throughput, fastest sending, but offers the lowest guarantee. Data might be lost if the broker crashes immediately after receiving the message but before persisting it, or if there's a network issue. Suitable for non-critical, high-volume data like some log metrics where occasional loss is acceptable. AX equals 1 leader acknowledgement. The producer waits for an acknowledgement from the leader replica of the partition. Analogy: sending a registered letter and waiting for a signature from the postmaster before you leave the post office. When to use offers a good balance between throughput and durability. The event is safely stored on the leader broker's disk. However, if the leader fails before its followers have replicated the message and a new leader is elected, the message could be lost. This scenario is rare but possible. AX equals all full consistency. The producer waits for an acknowledgement from the leader and all in-sync follower replicas. In sync means the followers have caught up and fully replicated the message. Analogy: sending that registered letter and waiting for signatures from the postmaster and 2 trusted deputies, confirming they all have a copy. When to use, this provides the strongest durability guarantee. Data loss is extremely unlikely as the message is persisted across multiple brokers. This is generally recommended for critical data where no loss is acceptable, e.g., financial transactions, order processing. The trade-off is slightly lower throughput due to the increased latency of waiting for multiple acknowledgements. It's common practice to use AX equals all for critical data, and AX equals 1 or AX equals 0 for less critical, high-volume data, depending on the application's specific requirements. 6.3 Consumer Guarantees, Delivery Semantics and Offsets. When a consumer reads events from Kafka, it needs clear semantics about how those events are delivered. Kafka offers 3 main delivery guarantees, which are largely controlled by how the consumer manages its progress. 6.3.1 Consumer Offsets. The bookmark. Every event within a Kafka partition has a unique, ever-increasing identifier called an offset. This is simply its position in the ordered log of events for that partition. Consumers use this offset to track their reading progress. When a consumer processes an event, it commits the offset of that event or the next event to be read. This is like updating a bookmark in a book to mark where you left off. If the consumer application stops or crashes when it restarts, it can pick up right from the last committed offset, ensuring it doesn't reprocess events it already handled and doesn't miss any new ones. The ability to control offset committing is what allows Kafka to offer different delivery semantics. 6.3.2 Delivery Semantics. At most once, concept, each event is processed either 0 or 1 time. The event might be lost if the consumer crashes after committing its offset, but before fully processing the event. Analogy: you mark your next reading page, commit offset before you read it. If the power goes out before you finish reading the page, you won't know if you read it, and you'll skip it when you pick up your book again. How it works. Consumer commits the offset immediately upon receiving the event, even before processing it. Use case: scenarios where missing a single event is acceptable, but duplication is not, e.g., some logging applications where a lost log line is less problematic than an erroneous duplicate. At least once. Concept: each event is guaranteed to be processed at least once. It might be processed more than once if the consumer crashes after fully processing the event, but before committing its offset. Analogy: you mark your next reading page, commit offset after you finish reading the current page. If the power goes out after you finish reading, but before you mark the page, you'll reread that page again next time. How it works. Consumer processes the event and then commits the offset. This is the default in Kafka and generally the most common pattern. Use case: most applications where retaining all data is critical, even if it means handling potential duplicates. Applications consuming data at least once typically need to be idempotent, meaning processing the same input multiple times has the same outcome as processing it once. Exactly once. Concept: each event is guaranteed to be processed exactly 1 time, even in the event of producer, consumer, or broker failures. This is the holy grail for many data processing systems. Analogy: not only do you mark the page perfectly after reading, but your actions are recorded such that if the power goes out, the book state and your progress are perfectly restored as if nothing happened. How it works. This is achieved through a combination of techniques: Kafka's transactional API for producers and consumers, and careful management of state and intermediate results. It typically involves writing both the outcome of the processing and the consumer's offset within a single, atomic transaction. Use case: critical applications like financial transactions, inventory management, or any scenario where reprocessing duplicates could lead to incorrect numbers or unwanted side effects. Exactly once processing adds complexity and some overhead, but is invaluable when strict data integrity is required. Kafka provides the necessary mechanisms, like the producer's AX configuration and the consumer's offset management, coupled with transactional APIs for exactly once, to achieve these various levels of guarantees. By understanding these options, developers can make informed decisions to build streaming applications that align with their specific data integrity requirements and tolerance for potential data loss or duplication. These guarantees are what make Kafka a reliable foundation for modern event-driven architectures. 7 Practical applications, real-world use cases of Kafka. We've explored what Apache Kafka is, how its core components function, and how it provides strong guarantees for data integrity. But the real power of Kafka shines through its immense versatility and its ability to solve pressing challenges across a wide range of industries and use cases. It's not just a technical curiosity, it's a foundational piece of infrastructure for many of today's most innovative and data-intensive companies. Let's look at some generalized scenarios to illustrate how Kafka is being used to transform businesses and unlock the value of real-time data. 7.1 Metrics and centralized logging aggregation. One of the earliest and most widespread applications of Kafka is as a conduit for operational intelligence. Modern applications, especially those built using microservices architectures, generate vast quantities of logs and metrics. These tell you what's happening within your systems, helping you monitor performance, diagnose issues, and ensure everything is running smoothly. The challenge: before Kafka, collecting logs and metrics from hundreds or thousands of servers and applications scattered across different environments was a complex, often fragile process. Each application might send its data directly to a logging system or a metrics database, leading to a tangled web of integrations, potential bottlenecks, and data loss during peak loads. Kafka's solution: Kafka acts as a central, highly scalable ingestion layer. All applications can simply publish their logs and metrics to dedicated Kafka topics. Think of these topics as giant, highly available streams for all your operational data. From Kafka, various downstream systems can then consume this data, real-time monitoring tools, to visualize dashboards, trigger alerts, and provide immediate visibility into system health. Data warehouses lakes, for long-term storage and historical analysis of trends. Security information and event management, SIEM systems, for detecting anomalous activities or security breaches. Case study: large-scale system monitoring. Imagine a global e-commerce giant with thousands of servers handling millions of transactions per minute. Each server generates logs about web requests, database queries, and internal processes. Historically, collecting these logs was a nightmare. By channeling all logs through a Kafka cluster, the company created a unified, real-time stream of its operational heartbeat. Their IT operations team can now build real-time dashboards to see active user counts, identify service outages within seconds, and understand the health of their entire platform, all powered by filtered and aggregated data flowing continuously from Kafka to their monitoring tools. 7.2 Real-time stream processing, from fraud to personalization. This is arguably where Kafka truly unlocks its transformative potential. By processing data as it arrives, businesses can react instantly to events, leading to immediate benefits. The challenge: traditional batch processing often meant that insights were stale by the time they were generated. Detecting fraud hours after a transaction or offering recommendations based on a customer's activity from yesterday significantly reduces effectiveness. Kafka's solution: Kafka provides the backbone for real-time stream processing applications. Events flow into Kafka, and stream processing applications often built using Kafka Streams or KSQLDB, which we'll discuss later, read these events, apply business logic, enrich them, aggregate them, and then produce new events or insights back into Kafka or to other systems. Case study: financial fraud detection. A major credit card company needs to identify fraudulent transactions as they happen, ideally before the transaction is even approved. They created a stream processing application using Kafka. Every credit card swipe or online payment attempt generates an event that goes into a payment attempts Kafka topic. The stream processing application continuously reads these events, combines them with historical customer spending patterns, also streamed from Kafka or a database, and applies machine learning models in real time. If a transaction deviates significantly from a customer's usual behavior, e.g., a small purchase in one city followed immediately by a large purchase across the globe, an alert is triggered, and the transaction can be flagged for review or even declined within milliseconds. This drastically reduces financial losses compared to post-facto detection. Case study: online retailer's recommendation engine. An online apparel retailer wants to enhance customer experience by offering highly relevant product recommendations. They leverage Kafka to capture every user click, view, search, and add to cart action as it happens. This real-time stream of user behavior is fed into a Kafka-powered recommendation engine. The engine continuously updates user profiles and product affinities, pushing personalized recommendations to the website as the user navigates, or sending targeted push notifications for items they've shown interest in but haven't purchased. This real-time personalization leads to higher conversion rates and increased customer engagement. 7.3 Event Sourcing and CQRS, Building Modern Systems. Kafka's nature as an immutable, append-only log makes it a perfect fit for a modern architectural pattern called event sourcing. The challenge: in traditional database systems, when you make a change, you typically update a record directly, overwriting the old state. This means you lose the history of how the state arrived at its current form. Debugging complex issues or auditing changes becomes difficult. Kafka's solution with event sourcing: instead of storing just the current state of an application, event sourcing stores every change as a sequence of immutable events. For example, for an order, you don't just store order status, shipped in a database. You store events like order created, item added to order, payment received, order shipped. Kafka provides the perfect durable log for these events. Benefits: you can reconstruct the state of any entity at any point in time by replaying all events up to that point. This dramatically simplifies auditing, debugging, and understanding complex business processes. CQRS, Command Query Responsibility Segregation. Event sourcing often goes hand in hand with CQRS. Commands, actions that change state, like place order, generate events stored in Kafka. Queries, requests for data, like show my order history, read from optimized read models, e.g., a relational database or search index, that are built by consuming events from Kafka. This separation ensures that complex writes don't impact read performance. Generalized use case: any complex business domain like logistics, banking, or gaming where maintaining a full historical ledger of actions and reconstructing state is crucial. 7.4 Data Pipeline ETL Modernization. Extract, transform, load ETL processes have been the backbone of data warehousing for decades. Kafka is fundamentally changing how these pipelines are built. The challenge: traditional ETL often involved batch jobs that extracted data from source systems, transformed it, and loaded it into data warehouses, usually overnight. This created latency and often required custom scripts for each integration point. Kafka's solution: Kafka acts as the central data bus for all data movement. Instead of batching data, change data capture, CDC, tools can read changes from source databases, e.g., new rows, updates, deletions, and stream them in real time to Kafka topics. From Kafka, this data can be continuously streamed into data warehouses, data lakes, search indexes, or other analytical systems. Case study: modernizing a traditional enterprise data warehouse. A large manufacturing company relied on nightly batch ETL jobs to update its central data warehouse. which summarized production metrics. Insights were always a day old. By implementing Kafka and using change data capture connectors, a Kafka ecosystem component, to stream database changes in real time into Kafka topics, they could then use stream processing to continuously transform and load this data into their data warehouse. Their business intelligence dashboards could now show production line performance, material usage, and defect rates updated every few minutes, enabling much faster operational adjustments and problem solving. 7.5 IoT and connected devices. The explosion of Internet of Things, IoT, devices means a flood of sensor data, often from geographically dispersed locations, needing to be ingested, processed, and analyzed in real time. The challenge: IoT devices can generate immense volumes of small, frequent data points. Traditional databases struggle with the ingestion rate, and simply storing everything can be cost-prohibitive. Analyzing this data for anomalies, predictive maintenance, or operational insights requires real-time capabilities. Kafka's solution. Kafka is ideally suited as the ingestion layer for IoT data. Devices can send their telemetry directly to Kafka topics. Its high throughput and ability to handle large numbers of concurrent producers are perfect for this. Once in Kafka, the data can be filtered, aggregated, and routed to various downstream systems. Real-time analytics, to detect anomalies, e.g., a sensor reading outside normal bounds or trigger alerts for critical events. Cloud storage, for long-term archiving in data lakes for offline analysis by data scientists. Control systems, to send commands back to devices based on real-time data, e.g., adjusting a thermostat based on room occupancy. Generalized use case, smart city infrastructure monitoring, traffic, pollution, industrial automation, predictive maintenance for machinery, connected vehicles, smart homes, and wearable health tech. These examples illustrate that Kafka is not confined to one niche. Rather, it serves as a powerful, flexible, and scalable backbone that enables businesses to truly harness the power of real-time data, driving innovation and efficiency across diverse domains. In the coming chapters, we'll delve into the specific components of the Kafka ecosystem that enable many of these advanced use cases. 8. Beyond core Kafka, Kafka Connect, and Kafka Streams. So far, we've focused on the foundational elements of Apache Kafka: its ability to reliably publish, store, and allow multiple applications to subscribe to streams of data. This core functionality is powerful, but Kafka's true strength as a platform for stream processing comes alive when we look at its rich ecosystem. Two particularly critical components that extend Kafka's capabilities significantly are Kafka Connect and Kafka Streams. These tools streamline common patterns in data integration and real-time processing, making it much easier to build sophisticated data pipelines and event-driven applications without having to write large amounts of custom code. 8.1 Kafka Connect, the universal data integrator. Think of Kafka Connect as a specialized framework designed to simplify getting data into Kafka from various sources and getting data out of Kafka to various destinations. It eliminates the need for you to write custom producer or consumer code every time you want to move data between Kafka and an external system like a database, a file system, or a cloud service. The problem it solves: imagine you need to continuously import customer data from a relational database into Kafka and simultaneously export processed events from Kafka to an analytics database or a cloud storage bucket. Without Kafka Connect, you would typically need to write and maintain custom code for each of these interactions. These custom integrations can be brittle, difficult to scale, and often require dealing with complex details like change data capture, schema evolution, and fault tolerance. How it works: sources and sinks, source connectors. These are pre-built or custom-developed components that read data from a source system, e.g., a database, a message queue, a file system, a web API, and write it into Kafka topics. They act as automated, continuous producers. Sink connectors. These are pre-built or custom-developed components that read data from Kafka topics and write it to a destination system, e.g., another database, a data warehouse, a search index, a cloud storage service. They act as automated, continuous consumers. Analogy, universal adapters. Imagine Kafka as a central hub with many different types of power outlets or ports. Kafka Connect provides an array of universal adapters. The connectors that allow various appliances, your source and destination systems, to plug directly into this hub, regardless of their native plug type. You simply choose the right adapter, configure it, and electricity data flows. Key benefits: pluggable architecture. Kafka Connect provides a framework to run connectors. You install the Connect runtime, and then you can deploy various pre-built connectors, e.g. JDBC for databases, FileStream for files, Amazon S3 for cloud storage, Elasticsearch for search indexes directly into it. Scalability. Connectors are designed to scale. You can run multiple Connect instances, workers, that distribute the workload of the connectors, ensuring high availability and fault tolerance. Managed offsets and transformations. Connectors automatically handle offset management when reading from Kafka and can perform light data transformations, like renaming fields or filtering records, before sending data to or from Kafka. Simplified integration. By providing standardized, production-ready components, Kafka Connect dramatically reduces the effort and complexity involved in building robust data pipelines. Example use case for Kafka Connect. A common scenario is using a JDBC source connector to read changes from a relational database and stream them in real time into Kafka topics. This enables change data capture, CDC. Then, an Elasticsearch sync connector can read from those Kafka topics and continuously index the data into an Elasticsearch cluster, making it instantly searchable. Meanwhile, an S3 sync connector can archive the same Kafka data into Amazon S3 for long-term storage and analytical processing. All this can be achieved with configuration, often requiring very little or no custom code. 8.2 Kafka Streams, building real-time stream processing applications. While Kafka Connect is about moving data into and out of Kafka, Kafka Streams is about processing that data within the Kafka ecosystem. It's a client library that allows you to build real-time applications and microservices that transform, aggregate, or enrich data streams directly from Kafka topics. The problem it solves: many applications need to do more than just move data. They need to analyze it, combine it, filter it, or react to patterns as they occur. For instance, you might want to count page views per minute, detect anomalous sensor readings, or join customer click data with their profile information in real time. Before Kafka Streams, this often required building complex, large-scale stream processing clusters with their own operational overhead, like Apache Flink or Apache Spark Streaming. How it works: a library for your application. Kafka Streams is not a separate cluster or service you deploy. Instead, it's a Java and Scala library that you embed directly into your own application's code. This makes it incredibly lightweight and flexible. Your application essentially becomes a Kafka client that reads from one or more input topics, performs computations, and then writes results to one or more output topics. Analogy: the smart data processor. Imagine you have raw ingredients data flowing on a conveyor belt, Kafka topics. Kafka Streams is like having a skilled chef with a set of precise tools. Functions like filter, map, aggregate, standing by the belt, continuously picking up ingredients, performing transformations, e.g., chopping, mixing, cooking, and then placing the finished dishes, processed data back onto another conveyor belt, another Kafka topic. This all happens in real time, ingredient by ingredient. Key benefits: lightweight client library, no separate cluster to manage. Your application runs wherever Java applications run, e.g., on a single server in a container on a VM. Scalable and fault-tolerant. Kafka Streams leverages Kafka's inherent scalability and fault tolerance. If you run multiple instances of your Streams application, Kafka Streams automatically distributes the processing workload across them, tied to partitions, and if one instance fails, another picks up its work. Stateful processing. Kafka Streams can manage and store state locally within your application, allowing for operations that require remembering past events, e.g., counting unique users over a time window or joining a stream of orders with a stream of customer profiles. It transparently uses Kafka for durable state storage, making it fault-tolerant. Developer-friendly API. It provides a rich, expressive API for common stream processing operations, making it relatively straightforward for developers to build powerful real-time applications. Example use case for Kafka Streams. Consider an application that needs to detect unusual login activity. You have a login-attempts Kafka topic. A Kafka Streams application can consume from this topic, maintain a temporary state of recent login attempts for each user, e.g., from different IP addresses. And if it detects multiple failed logins from new locations within a short timeframe, it can publish an unusual activity alert event to another Kafka topic. This alert can then trigger other systems, e.g., SMS notifications, account lockouts. Both Kafka Connect and Kafka Streams are powerful extensions that move Kafka beyond being just a data transport mechanism. Kafka Connect simplifies data integration with external systems, while Kafka Streams empowers developers to build sophisticated, scalable, and fault-tolerant real-time processing applications directly within the Kafka ecosystem. Together with Core Kafka, they provide a comprehensive platform for managing and leveraging data in motion. In the next chapter, we'll explore even more ways to simplify interaction and ensure data quality in this dynamic environment. 9. KSQL and Schema Registry, stream processing made easier. In the previous chapter, we explored how Kafka Connect and Kafka Streams significantly extend Kafka's capabilities for data integration and real-time processing. While Kafka Streams offers immense power and flexibility for developers, it requires writing code, typically in Java or Scala. For many tasks, especially for data analysts or those who prefer a more declarative approach, a code-centric solution can be a barrier. This is where tools like KSQL-DB, formerly KSQL, come into play, democratizing access to stream processing by allowing users to work with real-time data using familiar SQL syntax. Complementing this, Schema Registry plays a vital role in ensuring that the data flowing through Kafka remains well-defined, consistent, and compatible as systems evolve. 9.1 KSQL and KSQL-DB, the sequel for streaming data. Imagine being able to query and transform real-time data streams using the same language you use for your databases, SQL. This is precisely what KSQL-DB delivers. It's an event streaming database that allows you to build real-time applications and stream processing pipelines entirely with SQL. The problem it solves. Many organizations have data analysts or developers who are highly proficient in SQL, but might not be familiar with programming languages like Java or Scala required for Kafka Streams. Building stream processing applications traditionally involved a steep learning curve. Moreover, simpler transformations or aggregations sometimes didn't warrant a full-blown application deployment. How it works. Streaming SQL. KSQL-DB runs on top of Kafka. You interact with it by writing SQL queries directly against your Kafka topics. It treats Kafka topics as if they were tables, allowing you to perform operations like filtering. Select specific events based on certain conditions, e.g., fraudulent transactions beyond a certain amount. Transforming, changing the structure or content of events, e.g., calculating a total from individual line items. Aggregating, counting, summing, or averaging events over a time window, e.g., total sales per minute. Joining, combining data from multiple Kafka topics, e.g., joining a stream of customer clicks with a stream of product details. Materialized views, creating continuous, real-time tables, backed by Kafka topics and a local state store that are constantly updated as new events arrive. These can be queried like a database. Analogy. The dynamic spreadsheet. Think of KSQL-DB as a dynamic spreadsheet that lives on top of your flowing data. Instead of static cells, it has continuously updating rows representing events. You can write formulas, SQL queries, that process these rows as they appear, producing new, continuously updating results, much like how a sum formula automatically updates as numbers are added to a column. Key benefits. Accessibility. Widens the accessibility of stream processing to a broader audience who are comfortable with SQL but not necessarily with programming languages. Rapid development. enables faster iteration and deployment of stream processing applications for many common use cases. Operational simplicity. As a server that runs atop Kafka, it handles the underlying complexities of distributed stream processing, state management, and fault tolerance automatically. Stream Processing Database allows you to define streams, event logs, and tables, continuously updated views or aggregations of streams, letting you query data at rest and data in motion with a unified SQL interface. Example use case for KSQL-DB. An online gaming company wants to monitor player activity in real time. They have a player actions Kafka topic, where each event represents an action like login, level up, item purchased. Using KSQL-DB, they could easily write a query like, create table high-view players as, select player id count as actions per minute. From player actions, window tumbling, size 1 minute. Group BY player id, having count, 100 emit changes. This KSQL-DB statement continuously identifies player ids who perform more than 100 actions in any given minute, outputting them to a new Kafka topic or a continuously updating table, without writing a single line of Java code. 9.2 Schema Registry, the guard dog for your data. As data flows through Kafka, especially in an organization with many different teams and applications publishing and consuming events, maintaining data quality, consistency, and compatibility becomes paramount. This is where Schema Registry steps in. The problem it solves, without a central mechanism to define and manage the structure schema of messages, you can run into significant problems. Data serialization/deserialization issues. Producers might write data in one format, and consumers might expect it in another, leading to failures. Schema evolution challenges. If a team decides to add a new field to an event or change an existing one, how do all the downstream consumers know about this change, and how can they continue to operate without breaking? Lack of governance. No central place to view or enforce the structure of data in various topics. How it works. Centralized schema management. Schema Registry is a separate component, typically a res-tful service, that stores a versioned history of schemas for Kafka topics. Serialization/deserialization. It works hand in hand with Kafka clients, producers, and consumers. When a producer sends an event, it first registers or checks its schema with the Schema Registry. The data itself is then serialized, e.g., using Avro, Protobuf, or JSON schema in a way that includes a reference to its schema ID. When a consumer reads the event, it uses that schema ID to retrieve the correct schema from Schema Registry and deserialize the data, ensuring it understands the format. Schema evolution compatibility. Schema Registry enforces schema compatibility rules, e.g., forward, backward, full compatibility. This means you can define rules that prevent producers from publishing data in a format that breaks older consumers or vice versa. For example, a backward-compatible schema allows producers to add new fields while old consumers can ignore them. Centralized governance provides a single source of truth for all data schemas, improving data governance and discoverability. Analogy, the data grammar police. Think of Schema Registry as the grammar and vocabulary police for your Kafka topics. It provides a dictionary of approved words, fields, and ensures that everyone speaks the same language, uses compatible data formats. If someone tries to say something in a new way, it checks if the new way is understandable by older listeners or if older ways can be understood by newer listeners, enforcing rules to prevent miscommunication. Key benefits. Interoperability ensures that different applications and teams can reliably produce and consume data from the same Kafka topics. Data quality promotes well-defined, structured data, reducing errors and ambiguities. Simplified evolutions facilitates graceful schema evolution, allowing data structures to change over time without breaking existing applications. Debugging assistance helps identify and debug issues related to conflicting or malformed data schemas. KSQL-DB and Schema Registry are excellent examples of how the Kafka ecosystem builds on the core platform to make stream processing more accessible and reliable. KSQL-DB empowers users to interact with streams using a familiar language, while Schema Registry ensures that the underlying data streams themselves are well-governed and compatible, fostering a robust and evolving data architecture. 10. Deploying and monitoring Kafka, a high-level overview. By now, you should have a solid conceptual understanding of what Apache Kafka is, how its core components function, and how its rich ecosystem expands its capabilities. But knowing how it works conceptually is one thing. Bringing it to life and ensuring it runs smoothly in a production environment is another. While this book won't dive into the nitty-gritty of specific installation steps or command line configurations, it's crucial to understand the high-level considerations involved in deploying and monitoring Kafka. Deploying Kafka means setting up its servers, brokers, and related components to create a functioning Kafka cluster. Monitoring means keeping a vigilant eye on that cluster to ensure its health, performance, and reliability. 10.1 Deployment Options, bringing Kafka to life. There are several ways to deploy and run an Apache Kafka cluster, each with its own trade-offs regarding control, convenience, and cost. 10.1.1 Self-managed on-premises or cloud VMS. This is how Kafka was traditionally deployed. You acquire or provision your own servers, physical machines in your data center, or virtual machines in a cloud provider like AWS EC2, Azure VMS, or Google Cloud Compute Engine. You then manually install and configure the Kafka software, along with Zookeeper for older versions, or manage the Karaft process for newer ones. Pros: full control. You have complete control over every aspect of the Kafka installation, configuration, and underlying infrastructure. Customization. Ideal if you have very specific security, networking, or performance requirements that managed services might not support. Cost efficiency, potentially. For very large-scale or long-term deployments, managing it yourself might be more cost-effective if you have existing infrastructure and expertise. Cons: high operational burden. You are responsible for everything: hardware provisioning, software installation, patching, upgrades, backups, disaster recovery, security, monitoring, and troubleshooting. This requires a dedicated team with significant expertise. Complexity: scaling, rebalancing, and maintaining high availability can be complex operations, requiring deep knowledge of Kafka's internal mechanisms. Time-consuming. Setting up and maintaining a production-ready Kafka cluster can be a time-consuming endeavor. 10.1.2 Container Orchestration, Kubernetes. As containerization, like Docker, and orchestration platforms, like Kubernetes, have become standard, deploying Kafka in these environments has gained popularity. You package Kafka brokers and related services into containers, and Kubernetes handles the deployment, scaling, and management of these containers across your cluster. Pros: portability. Containers make your Kafka deployment highly portable across different environments. Automation. Kubernetes automates many operational tasks like scaling, self-healing, and rolling updates. Resource efficiency. Can lead to better utilization of underlying hardware. Cons: complexity. While Kubernetes automates much, operating stateful applications like Kafka on Kubernetes still requires significant Kubernetes expertise. It's often referred to as operating an operating system. Steep learning curve. Both Kubernetes and Kafka are complex, and combining them requires deep knowledge of both. Maturity. While rapidly maturing, there are still best practices evolving for specific Kafka configurations on Kubernetes at scale. 10.1.3 Managed Kafka Services, Cloud Providers. For many organizations, especially those focused on application development rather than infrastructure management, managed Kafka services offered by cloud providers are an increasingly attractive option. These services handle the underlying infrastructure, provisioning, scaling, patching, backups, and often integrate security and monitoring directly. Examples: Confluent Cloud, a fully managed service from the original creators of Kafka, offering features beyond just core Kafka functionality, including managed Kafka Connect and KSQL-DB. Amazon MSK, managed streaming for Apache Kafka. Amazon's managed Kafka service. Azure Event Hubs for Kafka, Azure's managed Kafka-compatible service, Though it's fundamentally an event hub, it has a Kafka API layer. Google Cloud Pub Sublite. Google Cloud's Kafka-compatible option. Pros: reduced operational burden. The cloud provider takes on most of the heavy lifting of managing the Kafka cluster. You only focus on using Kafka. Faster time to market. You can spin up a production-ready Kafka cluster in minutes or hours, not days or weeks. Scalability and reliability. Built on the cloud provider's robust infrastructure, offering high scalability and availability with less effort from your side. Cost predictability. Costs are often based on consumption, making budgeting clearer. Cons: less control. You have less granular control over the underlying infrastructure and specific Kafka configurations. Vendor lock-in. While Kafka is open source, using a specific managed service might introduce some level of vendor lock-in due to API extensions or integrations. Cost: potentially. For very high-volume, continuous usage, managed services can sometimes be more expensive than self-managed options, depending on your internal operational costs. The choice of deployment option often depends on an organization's existing infrastructure, operational expertise, scale requirements, and budget. For many, the convenience and reduced operational overhead of managed services outweigh the desire for full control. 10.2 Monitoring Kafka. Keeping a finger on the pulse. Once Kafka is deployed, whether self-managed or through a cloud provider, continuous monitoring is non-negotiable. Kafka systems are often mission-critical, forming the central nervous system of data flows. Effective monitoring allows you to detect issues early, identify problems before they impact users or become critical, understand performance, analyze throughput, latency, and resource utilization. Plan capacity, forecast future needs, and scale your cluster proactively. Ensure data integrity. Verify that producers are sending data and consumers are processing it as expected. Here are some key areas and metrics to monitor conceptually. 10.2.1 Broker health and performance. CPU, memory, disk usage. Monitor the fundamental resource consumption of each Kafka broker. High CPU or memory usage can indicate a bottleneck, while high disk usage warns of storage limits. Network throughput. How much data is being sent and received by each broker. This is crucial for understanding overall data flow. Connection count. The number of active connections to each broker from producers, consumers, and other brokers. Request latency. How long it takes for brokers to process requests from producers and consumers. High latency indicates potential performance issues. 10.2.2 Topic and partition metrics. Message in out rate. The number of messages published to or consumed from each topic per second. This tells you the activity level of your data streams. Byte in out rate. Similar to message rate, but measured in bytes, indicating the volume of data. Partition leader status. Ensure all partitions have an active leader. If a leader goes down, a new one should be elected quickly. Under replicated partitions, URP, this is a critical metric. It tells you if any replicas are failing to keep up with their leaders, potentially jeopardizing data durability. A high URP count means your data is at risk. 10.2.3 Producer and consumer metrics. Producer throughput latency. Are producers able to send data to Kafka efficiently? Are there any bottlenecks client-side? Consumer lag, most critical consumer metric. This measures how far behind a consumer group is from the head of the Kafka log for a given topic. It's often measured in terms of messages or time. Analogy. Imagine a river. Consumer lag tells you how far upstream your raft is from the mouth of the river. If the river is flowing fast and your raft is moving slowly, your lag will increase. Importance. High or growing consumer lag indicates that your consumers are not processing data as quickly as it's being produced, which can lead to delayed insights, resource bottlenecks, or even data loss if the data ages out of Kafka's retention period before being processed. Consumer rebalancing. Monitor when consumer groups rebalance, as this can temporarily pause consumption. Frequent rebalancing might indicate issues within the consumer group or unhealthy consumers. 10.2.4 Zookeeper, if applicable, /Karaft metrics. Health and connectivity. Ensure the Zookeeper ensemble or Craft quorum is healthy and that Kafka brokers can connect to it. Latency. How quickly Zookeeper processes requests. Monitoring Kafka typically involves integrating specialized tools and platforms like Prometheus/Grafana, Datadog, ElkStack, or built-in dashboards provided by managed services to collect, visualize, and alert on these metrics. Proactive monitoring and alerting are essential for maintaining a stable and performant Kafka deployment, enabling prompt reactions to potential issues and predictable scaling as your data needs grow. 11. Security, scalability, and performance considerations. By now, you understand that Apache Kafka is a powerful and reliable distributed streaming platform. However, deploying and operating Kafka effectively for critical applications requires careful consideration of three paramount factors: security, scalability, and performance. These aren't just one-time configurations. They are continuous considerations that evolve with your data needs and the increasing sophistication of cyber threats. While Kafka is engineered for strength in these areas, realizing its full potential demands a thoughtful approach to its deployment and ongoing management. 11.1. Security. Protecting your data in motion. In an era where data breaches are common and regulations like GDPR and HIPAA are strict, securing your Kafka cluster is non-negotiable. Kafka, by default, assumes a trusted environment, but it provides robust mechanisms to secure data and access in more realistic, untrusted network conditions. Security in Kafka typically involves four main pillars. 11.1.1. Encryption, data in transit. The threat, eavesdropping or interception of data as it travels between your producers, consumers, and Kafka brokers. Kafka's solution. Kafka supports SSL/TLS, Secure Sockets Layer Transport Layer Security, for network communication. This encrypts the data as it moves over the network, ensuring that even if intercepted, it remains unreadable. You can configure SSL for client-to-broker communication, producers-consumers to brokers, and for interbroker communication, brokers talking to each other for replication. Analogy. Putting your mail in a sealed, tamper-proof envelope before it goes into the mailbox and during transit between postal sorting centers. 11.1.2. Authentication. Who are you? The threat. Unauthorized entities trying to connect to your Kafka cluster. Kafka's solution. Kafka offers several authentication mechanisms. SSL client authentication, where clients, producers, consumers present a valid SSL certificate signed by a trusted certificate authority to prove their identity. SASL, simple authentication and security layer, a framework that supports various authentication methods, including plain, username password authentication can be combined with TLS for security. Kerberos, a widely used network authentication protocol often found in enterprise environments. Scram, salted challenge response authentication mechanism, a more secure password-based authentication mechanism. Analogy. Requiring every person who wishes to send or receive mail to first present a valid ID to the postal service. 11.1.3. Authorization. What can you do? The threat. Authenticated users or applications trying to perform actions they are not permitted to, e.g., a logging application trying to write to a financial transactions topic. Kafka's solution. ACLS, access control lists. Once a user or application is authenticated, Kafka's authorization layer checks if they have permission to perform a specific operation, e.g., read from a topic, write to a topic, create a new topic, describe the cluster on a particular resource, e.g., a specific topic, a consumer group. Analogy. Even if you have a valid ID, you are only allowed to access specific mailboxes or perform specific mail services, send a letter, pick up a package based on your credentials. You can't just access anyone's mail or enter restricted areas. 11.1.4. Data at rest encryption. The threat. Physical theft of data disks or unauthorized access to data stored on the Kafka broker servers. Kafka's solution. While Kafka itself doesn't provide built-in encryption for data on disk, this is typically handled at the operating system level, e.g., using disk encryption like LUKS on Linux, BitLocker on Windows, or by cloud provider disk encryption services. The data stored by Kafka is immutable logs, which often simplifies this. Analogy: storing your physical mail records in a locked, fireproof safe within the postal sorting facility. 11.2 Scalability. Growing with your data. Kafka is inherently designed for horizontal scalability, meaning you can increase its capacity by adding more machines rather than requiring larger, more powerful single machines. However, effective scalability requires careful planning and continuous adjustment. Partitions are key. The number of partitions in your topics is fundamental to scalability. More partitions generally allow for more parallelism in both producing and consuming data. Adding brokers. As your data volume grows, you can add more Kafka brokers to your cluster. Kafka will automatically rebalance existing partitions to take advantage of the new capacity, distributing the load and allowing for higher throughput. Consumer group scalability. To handle increased consumption load, you simply add more consumer instances to your consumer group. If you have 10 partitions, you can scale a consumer group up to 10 instances, with each instance processing one partition. Adding more instances beyond the number of partitions won't help, as there will be no more partitions to assign. Resource monitoring. Continuous monitoring of CPU, memory, disk I/O, and network activity across your brokers and applications is crucial. Bottlenecks in any of these areas will indicate where you need to scale up, add more resources to existing machines, or scale out, add more machines or partitions. Auto-scaling in the cloud. Managed Kafka services in the cloud often offer auto-scaling capabilities, automatically adjusting the number of brokers or underlying compute resources based on load. Self-managed deployments can implement similar logic using orchestration tools. 11.3 Performance. Optimizing for speed and efficiency. Achieving optimal performance with Kafka involves a balance of configuration, infrastructure, and good application design. Message size. While Kafka handles large messages, smaller average message sizes generally lead to higher throughput as more messages can be processed per unit of time. Batching producers. Producers can significantly improve performance by sending messages in batches rather than individually. This reduces network overhead and improves throughput. There are configurations for the number of messages to batch or the time to wait before sending a batch. Compression. Kafka supports various compression algorithms, e.g., gzip, snappy, LZ4, zstandard. Compressing messages reduces the amount of data transferred over the network and stored on disk, improving both throughput and storage efficiency at the cost of some CPU usage for compression-decompression. Consumer polling. Consumers poll Kafka for new messages. The polling interval and the maximum number of messages fetched in a single poll are configurable and impact consumer latency and throughput. Disk subsystem. Kafka is highly dependent on disk I/O using fast disks, like SSDs. Configuring appropriate RAID levels and ensuring sufficient disk throughput are vital for sustained performance. Network configuration. A high-bandwidth, low-latency network between your producers, consumers, and Kafka brokers is essential. Network saturation is a common bottleneck. JVM tuning. Since Kafka is a Java application, tuning the Java virtual machine, JVM, memory settings, and garbage collection can have a significant impact on broker performance and stability. Avoiding hot partitions. If all events with a specific key, e.g., a hot user ID, are routed to a single partition, that partition can become a bottleneck. Distributing keys more evenly or repartitioning data can help alleviate this. In conclusion, while Kafka provides the building blocks for secure, scalable, and high-performance data streams, the responsibility lies with the system architects and operators to properly configure, monitor, and manage these aspects. A well-secured Kafka cluster ensures data integrity, a scalable one adapts to growing demands, and a performant one delivers data at the speed your business requires. Master these three, and your Kafka deployment can become the reliable backbone of your real-time data architecture. 12. The future of stream processing. Kafka's evolving role. We've journeyed through the intricate world of Apache Kafka, from understanding the foundational need for real-time data streams to exploring its core components, its ecosystem tools, and the critical considerations for its deployment and operation. We've seen how Kafka acts as the central nervous system for data, enabling organizations to react to events as they unfold, not hours or days later. But what does the future hold for Kafka, and more broadly, for stream processing in general? The landscape of data architecture is constantly evolving, driven by new technologies, increasing data volumes, and ever greater demands for immediacy and intelligence. Kafka is not just keeping pace. It's actively shaping this future. 12.1 Kafka as the backbone of event-driven architectures. Perhaps the most significant trend Kafka is leading is the shift towards event-driven architectures, EDAs. In a traditional request-response model, services communicate directly with each other. In an EDA, services publish events to a central event log, Kafka, and other services react to those events. Decoupling. Services become highly decoupled. A service doesn't need to know who will consume its events, only that it publishes them correctly. This greatly increases agility and resilience. Scalability and resilience. If one service fails, others can continue to operate and process events. New services can be added easily by simply consuming from relevant topics without modifying existing systems. Auditability. The immutable, persistent nature of Kafka's log provides a comprehensive audit trail of every significant action that has occurred in an organization. Microservices communication. Kafka has become the de facto messaging backbone for many microservices deployments, enabling independent services to communicate asynchronously and build complex functionalities out of simpler, distributed components. The future will see even broader adoption of EDAs, moving beyond internal enterprise applications to power interactions between businesses and forming the basis of hyper-connected digital ecosystems. 12.2 Integration with data lakes and cloud platforms. The rise of the data lake as a centralized repository for vast amounts of raw, diverse data has been another major trend. Data lakes, often built on cloud storage services like Amazon S3, Google Cloud Storage, or Azure Blob Storage, provide flexible, scalable, and cost-effective storage. Kafka plays a crucial bridging role here. Real-time ingestion. Kafka serves as the real-time ingestion layer for data lakes. Events from operational systems, IoT devices, and applications are streamed into Kafka and then continuously loaded into the data lake using Kafka Connect. This eliminates batching delays and ensures the data lake always contains the freshest information. Data lake activators. Data from the lake can also be streamed back into Kafka for real-time analytics, dashboards, or to drive operational applications. This turns the data lake into an active, rather than just a passive repository. Cloud providers themselves are heavily investing in managed Kafka services, like Amazon MSK, Azure Event Hubs for Kafka, Confluent Cloud, recognizing Kafka's central role. This trend simplifies deployment and management for organizations focusing on their core business rather than infrastructure. The movement towards serverless and cloud-native Kafka deployments is also gaining momentum, further abstracting away infrastructure concerns and allowing users to pay only for actual consumption. 12.3 Beyond pure data. The event as a business object. Increasingly, organizations are recognizing that the event itself is a first-class business object, not just a technical artifact. This leads to concepts like event streaming platforms, where Kafka is seen as the central nervous system for an entire business's operations. Business intelligence. Real-time event streams provide instantaneous business intelligence, allowing companies to respond to customer behavior, market changes, or operational incidents with unprecedented speed. Proactive operations. Predictive analytics and machine learning models, often trained on historical event data and applied to live streams via Kafka Streams or KSQLDB, are enabling proactive rather than reactive operations. Think predictive maintenance, fraud prevention, or personalized marketing campaigns that adapt live. Contextual data. The ability to join and enrich real-time event streams with static or slow-changing context data, often stored in external databases or caches, allows for richer, more informed real-time decision-making. 12.4 Ethical considerations and the ever-expanding ecosystem. As data becomes more central and real-time, the ethical implications of data collection, processing, and usage come to the forefront. Discussions around data privacy, algorithmic bias, and the responsible use of real-time insights will continue to shape how event streaming platforms are designed and governed. Kafka's inherent transparency, immutable logs, auditable offsets, can be a strength in meeting these challenges, but responsible application development remains key. Finally, the Kafka ecosystem continues to grow at an astonishing pace. New connectors, stream processing libraries, monitoring tools, and specialized services are constantly being developed by the open-source community and commercial vendors. This vibrant ecosystem ensures Kafka's adaptability and continued relevance in a rapidly changing technological landscape. In conclusion, the enduring power of stream processing, Apache Kafka has revolutionized how organizations handle data, shifting the paradigm from static batch processing to dynamic, real-time event streams. It has moved from a niche technology for big data companies to a mainstream, foundational component for any enterprise aiming to be data-driven and responsive in today's fast-paced digital world. Its core principles, distributed, fault-tolerant, high-throughput durability, coupled with its expansive ecosystem for integration and processing, ensure its enduring power. Whether it's powering mission-critical financial systems, personalizing your online shopping experience, or gathering data from millions of IoT devices, Kafka is the unsung hero, enabling the continuous flow of information that defines our modern technological age. Understanding it is not just about comprehending a technology, it's about grasping the future of data.